Hello and thank you for watching this video. My name is Halima Najibi. I'm a PhD candidate at the Embedded Systems Laboratory in IPFL, Switzerland. I will be presenting my work, which is a collaboration with the Polytechnical University of Madrid, which is entitled Enabling Optimal Power Generation of Flow Cell Arrays in 3D MPSoCs with On-Chip Switched Capacitor Converter. For the following 15 minutes, I will first introduce the flow cell array technology and the motivation behind this work. Then I will briefly talk about the on-chip converter design process. Next, I will present the setup used in our experiments, and I'll show you some results that highlight the importance of the work before concluding this video. So let's start with the introduction. Nowadays, many data-intensive applications necessitate high computing power and high data transfer rates, and they often run in multiprocessor platforms, or MPSoCs, that can contain multiple CPUs. They contain GPUs, application-specific accelerators, and also different types of memories. In two-dimensional MPSoCs, the scaling of global interconnect wiring remains a major bottleneck due to the communication delays and also due to the power dissipation. Therefore, 3D integration using through-silicon via technology, or TSVs, offers the advantage of vertical scalability, heterogeneity, and high communication bandwidth between 3D MPSoC layers. However, 3D integration is limited by heat dissipation due to higher power densities and also by the additional complexity of power delivery. In this context, as a solution to these challenges, we propose to use the flow cell array technology, or FCAs. The FCAs consist of microchannels that are etched in the silicon substrate of 3D MPSoC dies, and these channels contain an electrolytic solution which flows inside and serves two main purposes. First, the liquid absorbs the heat that is generated by the activity of the dies and serves as on-chip liquid cooling. And second, the electrolyte inside the channel electrochemically reacts to generate an electrical current that can be used to partially power the logic gates. This technology has been prototyped, and an electrochemical model of the FCAs was developed and validated against real measurements, which allows to thermally and electrically simulate 3D MPSoCs with FCAs. The FCAs are integrated as part of the power network of 3D MPSoCs as an additional power source. In a previous work, we proposed to directly connect them to the metal lines of the power grid, which allows to reduce up to 20% of voltage drop for a high-performance processor. And also, it does not necessitate any additional area requirements because FCAs do not occupy any active area. To model the impact of FCAs on power supply of 3D MPSoCs, we developed a thermally aware compact SPICE model based on the voltage-power relation of the flow cells, which is obtained using the electrothermal simulators that I mentioned in the previous slide. However, if we look at the voltage-power dependency of FCAs, we observe that the peak power generation corresponds to a voltage between FCA electrodes around 0.6 volts, while for targeted high-performance applications, the operation voltages are often between 0.9 to 1.1 volts. And hence, directly connecting FCAs to the power grid leads to a suboptimal FCA on-chip power generation. Which brings me to the main contribution of this work, that is, using voltage regulators in order to optimize the operation voltage of flow cell arrays and therefore enhance the on-chip power generation regardless of chip operation voltage, as it is shown in the figure. Then we explore different configurations in terms of number of flow cells connected to a single converter in order to optimize the total converter area requirement. And finally, as converters enable switching on and off FCA power generation depending on processor utilization, we show that by doing so, we can increase the lifetime of the reservoir, which contains the electrolytic liquid flowing inside the FCA channels. As I mentioned earlier, we use the voltage regulators to supply the optimal voltage, namely 0.6 volts, to FCAs. By doing so, we also decouple them from the logic circuit, and we allow to keep a constant voltage level in case of supply noise and transient load changes. We use, for our case, the switched capacitor or SC converter technology because it is easier to integrate in IC design, contrary to inductor-based converters. The SC converters also have a high conversion efficiency, around 80%, and their area overhead is much lower. And to match the voltage conversion ratio needed for our application, we design a 1:2 switched capacitor converter, which only uses 4 transistors and 1 capacitor. And we use the 28 nanometer CMOS technology to model it. Further details on this particular converter topology and, in general, switched capacitors can be found in the references of the published paper. To emulate the FCA power generation using SC converter, we develop a circuit model of the converter, as shown in the picture. It comprises 2 resistances, Ri and Rv, which model the conduction and switching losses in the circuit, and a capacitor, which models the dynamics of the circuit. These model components are determined based on the target application, which in our case are the input and output voltages. And once they are determined, the physical design parameters of the circuit need to be adjusted to match the desired converter model, namely transistor sizing, determining the resistances, and the capacitor sizing and switching frequency for the dynamics. And hence, we perform a design space exploration to choose the SC configuration with the desired performance. We calculate the SC conversion efficiency, the output power, and the total converter area for a large number of configurations, as shown in the figure, and we see here a clear trade-off between efficiency and total area, as the sizing of the components directly affects the power losses in the circuit. And for the case of our application, we select the converter configuration that has the lowest area while keeping the maximal possible conversion efficiency and therefore output power. To simulate the FCA and the converter performance, we use a 3D MPSoC model which comprises a processor layer which has the IBM Power 8 power profile and a memory layer containing 4 second-generation HBM memories. The power delivery and the inter-layer communication is done using TSVs. And in these 3D MPSoCs, the FCAs are etched in the silicon substrate of both layers, and the converters connect them to the power delivery grids of the dies. We use a power delivery network structure where the TSVs are grouped in island, each supplying VDD to an independent subgrid, and the signal TSVs are also placed to ensure the memory bandwidth. Then FCAs are etched in the remaining area in the silicon substrates of the dies, and we connect each 200 micron long section of the channels to one single converter. The dimensions used for the FCAs are 100 microns of height and 50 microns of width, and they have a pitch of 100 microns. And the TSVs have a diameter of 5 microns and a pitch of 10 microns. And finally, the VDD is set to 1.1 volts, which corresponds to the processor high-performance mode. In our simulations, we analyze the FCA power generation and converter efficiency in case of the processor, as it generally has a higher power consumption and suffers higher voltage drops than the memories. However, the memories contribute to the temperature increase of the whole 3D system. To model the different processor load scenarios, we use real measured power maps where the cores switch between different load scenarios. For instance, in power map 1, all the cores are in nominal frequency, and in the other power maps, 6 cores are operating in maximal frequency and 6 others are idle. And this allows us to evaluate the FCA and SC converter efficiency for multiple output power density scenarios. Our simulation results show that the switched capacitor converters are able to provide a stable and optimal operation voltage to FCAs and maximize their on-chip power generation. In particular, using the converters enables up to 120% higher FCA power generation compared to directly connecting them to the 3D MPSoC power grid. In all the output load scenarios, namely the cores being idle in nominal frequency or in maximal power, the converter efficiency remains higher than 80% as shown in this table. And finally, the output power of the converter is over 85% higher than the output power of the FCAs when no switch capacitor converter is used. In the previous simulations, we connected each 200 micron long flow cell to a single converter, which required a large number of converters. Therefore, we now propose to decrease the number of converters by connecting multiple FCA sections to a single one. In this case, the new input power density will be proportional to the number of connected flow cells, and the converters need to be resized to match the minimum area and highest efficiency requirements. In our experiments, we connected 4 to 36 flow cells to each converter, and we observed that the area requirements in terms of total chip area percentage is lower as the number of connected flow cells increase. However, the maximum voltage drop increases as well due to longer wires between the FCAs and the output loads. Yet, we are able to connect up to 25 flow cells to one regulator while maintaining the voltage drop or IR drop below 5%, which corresponds to 55 millivolts for our VT, and the total area requirement stays around 1% of total chip area. Having covered the physical design aspect, the next effort is to manage the durability of FCAs. As the on-chip power generation is due to electrochemical reactions between the liquid electrolytes, using FCA power causes a reduction of the number of reactants over time. In addition, a crossover occurs between the fuel and oxidant for membraneless channels, which also affect the concentration of the reactants in the FCA liquid reservoir, even in an open circuit where no reaction happens. But in general, the on-chip power generation degrades up to 100 times more the electrolyte's concentration than the mixing along the channel. Therefore, as the converter inherently enables disconnecting FCAs from the power delivery network, we propose to dynamically do so depending on chip activity, which allows to stop unnecessary reactions when no extra power is needed. We calculate the lifetime of the reservoir containing the FCA liquid for different duty cycle levels of the processor when dynamically switching off the FCAs versus when they are always on. So when the processor is idle and the FCAs are disconnected from the power network, the degradation of the electrolytic liquid in that period of time is low, as it only is due to the fuel and oxidant mixing. However, if the FCAs continue to generate power during that time, the degradation of the liquid happens at almost the same rate as when the processor is at 100% duty cycle. Now, to put this into perspective, the red curve shows that the dynamic switching allows to extend the lifetime of the FCAs by 1.8 times for a duty cycle of 50% and by 4.5 times for a duty cycle of 20%. To summarize this presentation, we have used in this work switched capacitor converters in order to optimize the operation voltage of flow cell arrays, regardless of chip VDD. We have showed that they enable over 1.9 times improvement of on-chip power generation compared to directly connecting FCAs to the chip power network. Additionally, we lowered the total converter area requirements down to 1% by connecting multiple flow cells to each converter, and while maintaining a maximum of 5% IR drop. And finally, we showed that dynamically switching off FCAs using voltage regulators allowed us to extend the lifetime of the FCA liquid reservoir. Thank you for watching this video presentation. If you have any questions, feel free to send me an email. And of course, for further details on the work, please refer to the published paper.